All right. So up to last Wednesday, we looked at series resonance. We looked at, in looking at it, we developed a number of formulae, but all of those formulae were related to or were derived from series resonance. Today, we want to start by talking about parallel resonance and expanding the principles that we learned last week. I want to expand them a bit, all right? So, in terms of parallel resonance, here we have an RLC parallel circuit. And I know I'm going to go a little quickly because I am aware that most of what I'm going to be saying, you already have it on the printed notes that, that I have provided you with. So the assumption here is that all these elements are pure elements. So we have a pure resistor, pure inductor, pure capacitor. And I can tell you up front that this is not necessarily true. Based on how a coil is made, an inductor is made, it inevitably would have resistance, all right? But be that as it may, we assume pure elements. If they are pure, then we can look at the admittance for each, going back to our AC circuits. So the admittance for the resistive portion would be 1 over R, which is G. For the inductive, it would be 1 over JXL, which would be minus JBL. And for C, YC would be 1 over minus JXC, which would give us JBC. So if I were to find the total admittance, we know from AC circuits that the total admittance would be YR plus YL plus YC, all right? And making the substitution, it means that YT is equal to G minus J into BL minus BC. Okay? Now, when we looked at series resonance, what we said was that resonance occurred where XL was equal to XC. And that's true. That's true. Now that I'm moving on to parallel resonance, I'm going to add, per se, something else in describing the circumstances under which resonance occurs. And here we say that at resonance, the reactive portion, so the reactive portion of the circuit impedance, and this is also true for the circuit admittance, all right? So the reactive portion of the circuit impedance or admittance is equal to 0. So if I go back to the equation that we just derived, right? Here's the equation. All right? Go back to that equation. At resonance, what we are saying is that the reactive portion, which is minus J into BL plus BC, or this is supposed to be minus. All right? All right, so that is minus JBL minus BC would be equal to 0. If we simplify that or make the necessary substitutions, BL, remember now, XL would have been 2 pi FL, all right? So it means that BL would be 1 over that. BC would be 1 over 2 pi FC. So it means that 1 over that would be 2 pi FC. All right? So it means that BL is equal to BC. Please note also that once we start describing the condition of resonance, we no longer use just F, but we indicate that this is FR, because this is true only at the resonant frequency. So if we were to rearrange this expression to make FR the subject, then FR is equal to 1 over 2 pi root LC. All right? However, this is the resonant frequency, and we are highlighting it for this parallel circuit. So this equation is true only for the circuit that we just looked at. Any question?
Sir, but the same thing for the series circuits.
I'm aware.
Sir, my assumption is because the XC and XL equals 0, sir, and for the series circuit.
No, what you said was wrong. XL and XC are not equal to 0. XL is equal to XC. That is for the series circuit. For the parallel circuit, BL is equal to BC. And that is true only for this circuit, this particular circuit, this one. All right? So for that circuit, or for this circuit, FR is equal to 1 over 2 pi root LC. Quite frankly, don't worry yourself about it because you won't be seeing that circuit again in this topic. But for the purpose of ensuring that we are clear with respect to the principle, the resonance principle, yeah, we're highlighting this fact. All right. Now, as I said before, the BL is equal to BC. Now, if the reactive portion is 0, then it means that the total admittance of the circuit would be equal to G. And we know that G is equal to 1 over R. So this admittance would be the minimum admittance because the JB part is 0. Right? So the minimum impedance admittance would be equal to G. All right? Now, if we have the minimum admittance would correspond to the maximum impedance. But you agree with that? Because remember now, impedance is the reciprocal of admittance, or the other way around, admittance is equal to the reciprocal of impedance. So if I have the smallest value possible of the admittance, it means that I will have the largest possible value of impedance. If I have the largest possible impedance, it means that I have the smallest possible current. So for parallel resonance, the minimum admittance corresponds to the maximum impedance. And if I have the maximum impedance, then it will be the minimum circuit current. There is a caveat, however, and that is the current within the circuit can be large. So the current that is passing through the inductor and the capacitor and the resistor, the current within the circuit can be large. All right, so the current can be large. However, the current flowing into the circuit is a minimum. So let me show you that on the figure. So what we are saying, IT, this current is the current flowing into the circuit. That is the current which is a minimum. These currents, we can't say anything about them. They can be very large. All right? So those currents can be very large. However, this current is a minimum. And you would understand because IL, since BL and BC would be equal, it means that IL and IC would be equal. However, they would be out of phase by 90. So when you add those two currents, yes, you will get 0. All right? And in this instance, for this circuit, and I keep stressing it, for this circuit, that minimum current will be based solely on R.
So when you add which two current, you will get 0. Can you repeat that last statement?
IL and IC. IL and IC. All right. Now, I did start out by, pardon? All right. I did start out by saying that we were assuming these elements to be pure elements, right? However, we have to deal with a more practical circuit. So for a more practical circuit, we have an inductor, a real inductor, and a real inductor will have some resistance, right? And it has some inductance. So that's the resistor. That's the inductor, right? So it's a more practical circuit. And this particular circuit with a variable capacitor here, a varicap, this particular circuit is known as a tank circuit, right? So for the tank circuit, which is more practical, we are going to apply the same principles I just applied to those three elements in parallel. Okay, so let us go. So here we have more practical circuit where we have an inductor which consists or has resistance in parallel with a capacitor. So how do we do the analysis? Again, we look at each branch. So we have an RL branch, and that impedance is R plus JXL. So we can find the admittance of this RL branch, right? And that RL branch is given as 1 over ZRL, which is 1 over R plus JXL. We have already given you this expression in AC circuits, but since we are on to resonance, we'll repeat it. So if we rationalize, we multiply by R minus JXL, and note that in rationalizing, I now make the substitution for XL. So XL we know is equal to omega L. So I'm just making that substitution here. All right, so we rationalize, and that's what we have. If I now look at the capacitive branch, so ZC would be equal to minus JXC. Again, we rationalize, so I would multiply by JXC. So I end up with JXC over XC squared, okay? So if I do that, simplify, then YC would be equal to J omega C. Again, I'm making the substitution because XC is equal to 1 over omega C. So if we find the reciprocal, we end up with our omega C. But of course, in rationalizing, we know that J squared is minus 1. So minus J squared is 1, all right? So we end up with J over omega C. Okay? So I can now find the total admittance of the circuit because I have the admittance for the RL branch. I have the admittance for the YC branch or for the C branch, right? So let's do that. So if we add the admittances, all right, I now get this expression. But as we just said, at resonance, the imaginary portion is 0. So I need to write YT in the form of A plus JB. And if I'm able to write it in the form of A plus JB, then at resonance, all we need to say is that B is equal to 0. So let's do that. Here we have two imaginary terms. We're just going to group them. All right. And having grouped them, we simplify and we take J outside the bracket. So at resonance, and note the shift, students. I've written YT, I've simplified it. At resonance, note omega L. I no longer write it as omega L. I now write it as omega R L. Omega C, I no longer write it as omega C. I now write it as omega RC, because this only happens, this reactive component is 0 only at resonance. Any questions? All right. All right, next. My objective is to find an expression for the resonant frequency. So it means I need to rearrange this equation to make omega R the subject. All right, so let's do that. So because that's equal to 0, we get the expression as shown. We multiply throughout. All right, so we just simply bring this up and bring that down. All right, so we get L over C is equal to R squared plus omega R squared L squared. Remember, the objective is to get a value or get an expression for F. So we need to start with R, all right? So simplifying, and then dividing throughout by L squared. So we get omega R squared to be equal to 1 over LC minus R over L all squared. But of course, we know that omega is equal to 2 pi F. So I can make the substitution to find F. All right. So omega R is equal to the square root of 1 over LC minus R over L all squared. Sorry. Can I go on? So FR will be equal to 1 over 2 pi square root of 1 over LC minus R over L all squared. So that's the expression for the resonant frequency. All right. I will just make the point, that this expression is this expression for the resonant frequency represent the forced resonant frequency of the circuit. The natural frequency is similar to that of the series circuit. So the question that was being raised earlier regarding those 3 elements in parallel, I think it was Mr. Bernard who raised the question. Right? What we are saying is that expression, the 1 over 2 pi root LC, represents the natural frequency. However, the forced resonant frequency was given by will be given by this expression. And again, students, I repeat ad nauseum that this expression represents the resonant frequency for this circuit. The circuit will look like this. No other circuit. All right? So this represents FR for the tank circuit. The tank circuit has an inductor in series with a resistor connected across a capacitor. Do I make myself clear? I take your silence to mean yes. All right, so we have the resonant frequency, but there is other information that we can get from the circuit. Yes, we know that at resonance, the reactive portion is equal to 0, but there's an active portion. Good. So the admittance at resonance will be given by the active portion. So there are a couple of things that are now similar to what we had with the series circuit. Based on the fact that we have no reactive portion, it means that there is no reactive power being dissipated at resonance, or the net reactive power. Let me be careful with how I say that. The net reactive power would be 0. Right? Because you will indeed have reactive power. It's just that the resultant, the net reactive power, would be 0. So the power dissipated in your circuit at resonance is purely active, as we saw with the series circuit. So that's 1. 2, based on the fact that it's resistive, yes. Well, coming from the power, it also means that the phase angle is 0, because the reactive portion is 0. So this admittance, yeah, would be the admittance of the tank circuit at resonance. However, if you look back in the derivation, this expression R squared plus XL squared, yes, that was equal to L over C. So let's look back at what you wrote earlier in the derivation. So L over C is equal to R squared plus omega L squared, all squared. So I can substitute for this into this expression. If I make the substitution, I get YT to be equal to RC over L. So that's YT, right? So YT is equal to RC over L, which means, therefore, that the impedance, because remember, when we introduce complex numbers and we introduce impedance and introduce admittance, etc., keep in mind, students, these are the complex numbers are concept. Admittance is a concept. You can't measure the reciprocal of an impedance. What you can measure is impedance. What you can measure is a current at a certain angle. But you can measure something on the real and imaginary axis. And I hope that is clear. So this impedance, ZT, for your tank circuit is known as the dynamic impedance of your circuit. Any questions?
Question, sir. Are you concerned with how we derive the formulas for the resonant frequency in the exam, or you just want the calculations from it?
It's totally up to you. If you want to try and remember them, then fine. But of course, if you run into a roadblock in terms of not remembering, then you could always derive. But I'm not testing you on your ability to derive. Eh? What we're interested in is that you know how to use the concepts. All right. So going back to the circuit, remember what we said before, that the current within the circuit can be much larger than the current flowing into the circuit. Okay, so the current within the circuit, in this instance, we have IC, we have IRL, right? Current into the circuit, we have IT. The ratio of these two currents, IC and IT. All right, the ratio of those two currents is known as the quality factor of your circuit. Now, we can determine IC and we can determine IT. So IC and IT, for IC, it is the applied voltage, right, which would be here. We have the applied voltage over XC. Again, XC is 1 over omega C. Now note, I'm very deliberate in this. Because all of what we're talking about is occurring at resonance. Note, I continue to use omega R, not just omega. For the current flowing into the circuit, we just derived the expression for the dynamic impedance. Now that's the impedance of the circuit at resonance. So we have V over ZD, where ZD is L over CR. So it means that for the current flowing into the circuit, we have VCR over L. When we find the ratio for quality factor, we get QR to be equal to omega L over R. So for your down circuit, the quality factor is similar in terms of the formula, is similar to that of your series circuit. Any questions? All right. So moving right along. So we have shown you a parallel circuit where we said that all three elements were pure elements. We tell you that that is impractical, right? We then showed you a practical circuit where you had a resistor, an inductor in parallel with a capacitor, but the inductor was now a practical inductor, which showed that it had resistance. We're going to step it up a bit, and now we look at a circuit where both the resistor and the capacitor have resistors. What else? Both the resistor, both the inductor and the capacitor have resistors in series. But the principle remains. What's that principle? Finding the total admittance. And just to note, if I had put in another reactance here, or another impedance, all right, the principle would remain the same. Meaning, because you know of a series component, you would find ZT. But you would find ZT in the form A plus JB. And at resonance, B is equal to 0. All right? Okay, so again, we find the admittance for the RL branch and the RC branch. All right. Now, we'll go through the derivation again because, as I said, we have given you this in AC circuits when we're looking at AC circuits on there, right? So for RL, that's the expression. For RC, that's the expression. All right. So again, as we did just now, we want to get the expressions in the form A plus JB. So I'm simply going to add YRL to YRC. And then we group imaginary and real. So if I do that, so this would be in the form, this would represent my A, and this would represent my B. So in this instance, we have A minus JB. So again, at resonance, the imaginary portion is 0. So it means that we equate those two. And the task from here on, once we substitute for omega, for XL and XC with omega, we simplify and make omega the subject. All right? Omega R. And then from that, we can find FR. All right, so simplifying. All right, so in substituting, note, because we're now at resonance, I immediately introduce omega R. So we are substituting for XL and XC. Now, just a trick to the trade, well, at least what I use. Note, I did not introduce omega too early. All right, so I use the X up to this point. Then I introduce omega. Of course, depending on your comfort with comfort level with math, you could still wait until you do the next step before introducing omega. I mean, it's totally up to you. There's no rule here. The only rule you need to note and to follow is that at resonance, well, first of all, you get it in the form A plus JB. And then you make B 0. That's all. That's the only rule.
I just want to get something clarified. When you started the class, you said the resonance at resonance, the reactive portion of the circuit impedance is 0. Is that for circuits that are considered pure, and for this one is the imaginary part at resonance equals 0?
All right. The imaginary portion is 0 under all circumstances. What I actually said at the start of the class is that when we did series resonance, what we simply said was that XC was equal to XL. That's what we said. And I went further to say what I'm now doing is to expand that to say that at resonance, the reactive portion is 0. And what that means is that when you get it in this form, the imaginary portion is 0. So this is true regardless of how the circuit looks. Whether you're dealing with series, whether you're dealing with series parallel, whether you have 5 branches in parallel, whether you have 12 branches in series and then in parallel, it doesn't matter. What you do is to get it in the form A plus JB and make the reactive portion 0. So cross multiplying and simplifying. bringing all this, the omega r terms together, because remember omega r is what we want. So we can bring this to the left-hand side and bring this to the right-hand side. If you do that, right, and then make our factorize, note that this, and let me be honest about something here. I'm going through all of this because I want it to look a particular way. But if you wish, you could have, instead of getting the LC, you could have simply divided the right-hand side by that. And you'd have had omega r. You with me? But I just want it in a particular way that will make understanding a little easier. So you would know that there's a pattern. So for this circuit, we have RL at the top and RC in the denominator. So you have RL squared minus LC. And this is just a way, to help you remember it if you need to remember it. Which means, therefore, that omega r is equal to 1 over LC times RL squared minus LC divided by RC squared minus LC, or FR is given by that expression. So just finding the square root, that's all. Okay? But we know that omega is equal to 2 pi f, so we divide through by 2 pi. Again, you could have left it like this, but I deliberately went ahead and wrote it like that, just to highlight the fact that this section would represent the natural frequency, but the complete expression represents the forced frequency.
Could you repeat that, sir?
Natural frequency, which is 1 over 2 pi root LC. Remember we spoke to that earlier? All right, but the complete expression represents the forced frequency of the circuit. The forced resonant frequency of the circuit. So at this stage, I can say to you that I have nothing further to say regarding the theoretical aspect of resonance. That's it. So we just do a couple problems, and then there are a couple that I need you to do and submit. All right. So take this question, please. All right. So let's see how we approach this now. Any volunteers? What's the first thing we need to do?
Draw the circuit.
Draw the circuit.
Okay.
Draw the circuit.
Now I know that so we have what 20 ohms, 710.61 microfarads. And we have variable capacitor. This is 20 volts, and this is 2 kilohertz. Okay. So now that we have drawn the circuit, the next question is, notwithstanding the fact that we know that, we are currently dealing with resonance, what is it about this circuit, about this question rather, that tells you that we are asking about resonance?
Supply current is minimum.
Good. So the current from the supply is a minimum. So that would tell you that the circuit is resonating. All right, so now that it is resonating, now that we know that the circuit is at resonance, what else do we need to know? Based on what we have before us, what else do we need to know?
So it's a tank circuit, sir.
So it's a tank circuit, beautiful. Good, so it's a tank circuit, and since it's a tank circuit, next. Come on, man, you guys on a roll. Where you stop for now? Come on, you guys on a roll. Where you stop for now? Yes. Next. So we know it's a tank circuit. What else?
Because we have
Impedance
So we know it's a tank circuit. What some more. I can't hear what you're saying.
Sir, because we know that it's a tank circuit and we are given the frequency and the resistance and inductance what we should do now is find the impedance of the known branch of the coil, sir. From there, transpose the frequency sorry, the frequency resonance frequency equation to find C, sir.
So how would you find
So
C
the
from
next
that?
step is to find the impedance. Okay.
So you're saying the next step is to find the
again, sir?
impedance? Go again, let me hear the step.
The impedance. The next step is to find the impedance in the coil. When we find the impedance in the coil, we can use the resonance frequency equation and transpose it to find the capacitor.
What equation would that be?
FR equal 1 over FR equal 1 over 2 pi square root 1 over LC minus R square over L square.
All right. So why then would I need to find the impedance of the RL branch?
Repeat that, sir. You break up all.
I'm saying, why would I need to find the impedance of the RL branch?
To get the admittance, sir.
Huh?
To
All right.
get
Let
the
me hear,
admittance, sir.
all right. Let me hear what Mr. Atkins is saying. He raised his hand.
Yes, sir. So based on the previous information you gave us before, omega r is equal to 1 over the square root of 1 over LC minus R squared over L squared, right? So of the frequency at resonance, so we could transpose for that to find C from the equation, basically.
Okay, which is what I was asking Mr. Mori, because there's no need for you to find the impedance of that branch. It doesn't advance the question in any way. So since you know it's a tank circuit, right, you can either seek to recall the equation for the resonant frequency or you derive it, right? But FR is equal to 1 over 2 pi square root of 1 over LC minus R over L all squared. Everybody okay with that? Is there anyone who has a problem with what we just wrote? All right. So we have here 2K. So that's 2 times 10 to the 3 times 2 pi. All right. And that's equal to the square root of 1 over LC minus R over L all squared. So we have 16 times 10 to the 6 pi squared is equal to 1 over LC minus R over L. Let me minus what was R? R was 20 over 710.61 times 10 to the minus 6 squared. Okay? Rearrange that for C. Whatever you get for C. I'm not gonna work that out for you. You can finish that. Have I lost anybody?
Sir, how do you get 16 from right there, sir? I don't know if I'm missing something or
Times
something.
2. 2 times 2. 4. 4, 4 is 16. Remember the square root is on the right-hand side, so I have to square both sides.
All right, sir.
Okay, once we have found the value for C, part B, how do we find the dynamic impedance?
L over RC.
Good. So ZD is equal to L over CR. All right, so that's part 2. Part 3, how do I find the supply current?
V over ZD, sir.
Good. So IT would be equal to V over ZD. And then finally, for the quality factor, Q is equal to
IC over IT.
all right, and that simplifies to,
Omega RL over R, sir.
okay, so that's omega R times L over R.
R.
So you leave out the space, I expect you to finish the question on your own. Is there anything that I have done, that I have said in relation to this particular question that is not understood? All right, good. So leave out the space and take the next question. Question 2. Go ahead for me, please. All right, now, for this particular question, we are told that the circuit is at resonance. Yeah. So the question is, how do we go about determining the current? What's the first step? Is my mic on? I need to double check. What's the first step? We want the circuit current. What information do we need to calculate current?
So, sir, the current would be equal to V over ZD.
Well, it's not a ZD because this is not a tank circuit.
Oh.
So what information would you need to calculate current? What additional information
Dynamic
do you need
impedance.
based on what you have here to calculate current?
RC.
The total impedance.
Okay, so you know that I.
Total.
Okay, so you know that I. So Murray, close your mic because you're using more than one device and you're disrupting the recording. So I is equal to V over Z. All right, so we wouldn't be specifying ZD, as I said earlier, because this is not the tank, right? Now, how am I gonna go about finding ZT? Circuit is resonating.
Well, we could recall the total admittance, and then from that we could get the real part of the equation, because since it's resonating, the imaginary would be equal to 0.
No, we're onto something good. All right. But there's a missing element, isn't there? Look carefully at the circuit. What's the missing element?
RC.
RC. How are you going to determine RC?
The 1 over 2 pi square root LC formula. The formula for frequency.
Huh?
The formula for frequency at resonance.
Which is?
1 over 2 pi square root LC times the square root of RL squared minus L over C over RC squared minus L over C.
All right. All right. So FR is equal to 1 over 2 pi. Yep. Square root of 1 over LC times, and if you get the first one right, which is the RL squared, then everything falls into place. All right. So from this, we find RC. Now you have one of two options. Once you have found RC, if you simply go ahead based on the circuit that you have before you, yes, once you have found RC and treat it like a regular AC circuit, then you'll be fine. All right. In other words, if you treat it like a regular AC circuit, you'll realize in working it out that the reactive portion is going to be equal to 0. All right. Or, as was recommended by Mr. Thomas, having found RC, you could then use the expression YT, because remember now, this is just the real portion you're interested in, would be RL over RL squared plus XL squared plus RC over RC squared plus XC squared, because this represented the real portion of the admittance. And from that, Z is equal to YT to the minus 1. Any questions?
Sure.
Yeah, man, I'm here.
So when you say total power, you mean apparent power or active power?
You tell me. What do you think?
So I think it'll be active power, sir.
Why?
If we're dealing with the real part.
What do you mean if you're dealing with the real part? Come on, man. Why? Why are you saying that? Anybody have an opinion on that?
Because there's no reactive power, sir.
Why, Mr. Gibbs?
Circuit is at resonance.
The circuit is at resonance and therefore the reactive portion is 0. And we have said it already, said it several times. It means that the only power that is there is active power. So to ask whether we should be talking about the apparent or the active is somewhat redundant because they must be one and the same. Because we are resonating, we only have active power. So it means that S would be equal to P plus J0. The theory can't change. Okay, gentlemen and ladies? The theory cannot change. And then part 3, going through each branch, you just treat them like regular AC circuit and you're fine. V over Z RL, V over Z R, over ZRC. All right? So Martin, you understand what I just said about the power?
Yes, sir.
All right. So, okay, so it is now 20 minutes to 1. Nobody else asking any questions, so I will now give you what I need you to be doing, which is, well, tell you what, we allow you to screenshot the next couple of questions. Fine. In the interest of time. So that's question number 1. By the way, before I say that, let me just make it abundantly clear how we're gonna proceed with these 4 questions I'm going to give you. These 4 questions. It is now 20 minutes to 1. I assume we will take another 15 minutes to write down these questions. These 4 questions are due in exactly 48 hours from now. The portal for uploading them will be closed at 5 minutes to 1 on Friday, April 1. What a day to have a closure of a portal. But anyway, it is Friday, the 1st of April. All right. I repeat, the portal will be open until 12:55, Friday, April 1. It will be locked thereafter. Do not write me send me any messages telling me that it closed at before time. Do not email it to me. I will simply ignore it. As a matter of fact, I won't ignore it. That's a lie. I will delete it. Do I make myself clear? Does anyone have any questions? Okay, so here are the questions. And once they are uploaded, you will get the solution. You will mark your own scripts and you will upload the marked scripts, which are total. While you do that, I will deal with the register. I would actually prefer if you screenshot what is here. Just to ensure that, you know, anyway. I really recommend that.
Screenshot, you can send it in the group.
All right, next question.
Sir, for this question, it only has two parts, A and B.
If that's what you see, yes.
Okay, sir.
Can't believe it. I can't get something easy. Eh?
Just making sure, sir.
All right. Um, let's go to question 3. That's question 3. All right, and a question. Just a minute, just a minute, just a minute. Okay, this is question 4. All right. We have all the questions. And I hope we have all the instructions. Just to make it clear, I know I did say that the primarily the good performances came from the Monday group, but I don't want to overshadow or not acknowledge that there were some good performances from this particular group. All right. So, Mr. Bernard, I'm acknowledging you, and I'm acknowledging Mr. Walker, who topped the class. I see Mr. Kelly, who have done well also. I think from this class, Mr. Sterling and Mr. Thomas. So I just want to be balanced. in acknowledging that there were some good performances from this group. Okay. So that said, I trust we will have a much more productive period going forward. There's one topic left, and then you will have your assessment. This is an administrative matter. Have you all been given your timetables or your timetable for all your modules for the end of semester exams?
No, sir.
Which modules haven't you received it for? Atkins?
Yes, sir. I have to check. I come back again. Sir. I have to check it and come back again. Sir. Sorry.
All right. Did you get a timetable? Is there anyone here who did not get a timetable? All right. So everybody got their timetable, and you have a schedule for networks, right?
No, sir, I didn't get any timetable.
All right. That's one of
Yes, sir.
34
Networks.
What's that, Mr.
So I
Thomas?
didn't.
On
Yeah, I
the
didn't get a
timetable,
timetable.
networks is
Yeah,
April.
Networks is what? April what?
April 28th.
Okay. All right. Okay then. All right, so we see you next week. We'll start complex waves then. All right. Miss Alexander, please stay on line. All right, thank you everybody. Take care.
All right, sir.